Hello, everyone, and welcome to another video review of a recent project that has been uploaded to the Digital Rocks portal. I have an exciting group here today, so hopefully you will enjoy the presentation, and I will let everybody introduce themselves. So I will start in order on my screen. Amogh, please, if you would start.
Sure. Hi, my name is Amogh. I'm a fourth-year PhD student at Penn State. My focus is informatics, information science and technology. I work on denoising of images, super resolution of images, and image processing in general in terms of signal to signal-based processing, digital signal processing. My research work is focused mainly on extracting information from noisy data. You could call it like solving the inverse problem most of the time. Yeah, thank you.
Thank you. Miral, would you introduce yourself?
Sure, yeah. Hello, everyone. I'm Miral Tawfik. I'm currently a reservoir engineer with Chevron, but this work has been done in collaboration with my supervisor, Dr. Karpyn at Penn State, and the other co-authors from Penn State as well.
Thank you. Zuleima?
Thank you, Masa. I'm Zuleima Karpyn, and I'm a faculty member at Penn State. I'm a professor of petroleum and natural gas engineering. I also have an administrative role. I'm associate dean for research in our college. I've had the pleasure to supervise the work that Miral and Amogh were doing in this piece of work, together with other group of collaborators, both from our Department of Energy and Mineral Engineering and Information Science and Technology at Penn State.
Well, thank you for joining us. Ankita and I here are hosting you. So Ankita, would you introduce yourself?
Yeah, thanks, Masha. So my name is Ankita. I am a data scientist in one of the mining companies here in Perth, in Australia. I finished my PhD back in 2020 from University of New South Wales, and my PhD was around X-ray images, working with grayscale and trying to understand the petrophysical properties that we could extract directly from grayscale images. And I've had the opportunity to work with Dr. Masha on with her Digital Rocks portal. Yeah, and I think that's one of the fun things I do apart from my work. So,
and Ankita continues to contribute both to curating and writing the newsletters, and I'm very thankful for that. Myself, my name is Masa Prodanovic, and I'm here in the role of a PI of the Digital Rocks board. So without further ado, Miral, if you would please go a little bit and tell us a little bit more about your project, and then we are going to have some questions.
Sounds good. Okay, thank you so much, Dr. Masa, for giving us the opportunity to highlight our data set that was recently posted on DRP. I have the reference for our data set and the paper associated with it down here. And before I start, I want to first acknowledge all the co-authors who are listed in the reference here. And we have Dr. Karpyn, of course, and Amogh with us on the call today. So this data set highlight is associated with a comparative study of traditional and deep learning denoising approaches for image-based petrophysical characterization of porous media. So first, I want to start with a quick motivation for this study. So in the bigger picture, we use CT images in a wide variety of applications in geoscience. Some of the most common use cases include understanding pore scale physics of processes like CCUS, enhanced oil recovery, and aquifer remediation. And over the years, there has been a huge improvement in image acquisition technologies, which combined with the computational advancements enabled an equally impressive development of image processing methods, including reconstruction, image enhancement, or denoising and image segmentation algorithms. And as with all computational methods, image processing algorithms are not 100% accurate. And in the literature, we see several studies that quantify the effect of different reconstruction and segmentation algorithms on the accuracy of petrophysical analyses, but very little has been done to compare denoising algorithms and understand their effect on petrophysical quantities in our domain specifically. So some of the questions that we try to answer in this study are: how will different denoising algorithms affect image-based petrophysical calculations? Is there one superior denoising algorithm that can be used for all petrophysical characterization? And how do we decide what is a good denoising algorithm? What kinds of metrics, or how do we evaluate a denoising algorithm? So can we decide it simply visually, or if the image looks clean, or using the traditional denoising metrics like peak signal to noise ratio, or do we need more physics-based evaluation metrics that's more specific to petrophysics? So to answer those questions, we have two data sets of brine, supercritical CO2, and glass system. The first data set, it's marked here as A, is a high exposure or high quality data set, which we take as a clean reference or baseline. And on the right, we have a lower quality or noisier version of the same data set, which was achieved by having a lower exposure time or conducting a faster scan. And if we look at the zoomed in features, we can get some idea of the types of errors that can result in our petrophysical analysis due to noise, like inaccurate porosity and saturation calculations. And it's even worse for interfacial properties like interfacial areas or contact angles, for example. So if we look, say here in just the first one, we see that there's a CO2 blob here and it's surrounded by brine on either sides. That's in the high quality image, but in the noisier version, it's very hard to see that boundary. So that will definitely affect our saturation quantification. Oops. Okay. So in this study, we compared 6 of the commonly used noise filters in our literature, including Gaussian, median, and non-local means, as well as deep learning-based denoising algorithms, including 3 fully supervised methods, which use the high-quality data set for one-to-one mapping while training. So we have noise to clean, RDN, and CCGAN, which represent 3 different architectures. And on the other extreme, we also assume a case where we only have the noisy version of the data and no high quality reference. So we have 2 fully unsupervised algorithms, noise to noise and noise to void. And to investigate the value of information, we also proposed a hybrid or semi-supervised method, which is somewhere between the noise to clean and noise to noise, as it uses a limited number of the high quality or reference images to denoise a larger low exposure data set. So here we tried using 75%, 50%, and 25% of the high quality data set as a reference. This can be useful, for example, when we need to scan the full length of the core at high resolution, but we have limited resources like limited time or on the scanner or limited budget. So we wanted to see if we can scan only a portion at high resolution and high exposure and use the low exposure time for the entire core while being able to maintain accurate petrophysical analysis through the semi-supervised denoising method. And so we compare all 14 denoising algorithms, first qualitatively, which is the most common evaluation method we saw in the literature. And we also compare it quantitatively using traditional denoising evaluation metrics like PSNR, SSIM. We also segmented the denoised data sets and used segmented images to conduct a physics-based evaluation, where we compare the calculated petrophysical properties for each denoised data set to the values calculated using the reference or the high quality data. So this includes bulk petrophysical properties like porosity and saturation, as well as pore scale properties like phase connectivity and specific surface area. So those are the results for the qualitative comparison. Here we see an XY slice for the high quality and low quality data set on the top left, as well as the same XY slice for each of the denoised data sets. Qualitatively or visually, we can see that the denoising algorithms have all resulted in a cleaner image compared to the low quality image. We can also see that within the traditional filters, which are all on the left, non-local means and SNN look the most promising. And we see that the deep learning algorithms, and particularly N2C, CCGAN, and N2N75 look extremely clean. But then if we inspect them a little bit closer, we can see marked by the blue and green circles that N2C and CCGAN, each of them has some features that are correct that are not correct in the other when we compare it to the reference image on the far left. And so this qualitative comparison is not necessarily going to get us to a point where we can select a good denoising algorithm. And so next we calculated the traditional evaluation metrics to get a more quantitative measure of the performance of the algorithms. In this table, each column represents an evaluation metric and each row represents a denoising algorithm. So if you look per column, the colors represent how well an algorithm is performing relative to the rest of the algorithms. And as we see in the scale on the right here, a green cell indicates a better performance, a red cell indicates a worse performance. I also highlighted the best performing value or denoising method based on each metric using the black boxes. So based on that, just to give a bigger picture, because there are nuances to each of the metrics, those are covered in the paper, but in general sense, we can say that there is not a single algorithm that performs the best across all metrics. We have, however, a worse performer among all metrics, and that's the noise to void method. It's an unsupervised method. We also see that fully supervised and semi-supervised algorithms are the best performers in all of the traditional evaluation metrics except blurring index, where SNN, which is a conventional noise filter, is the best performer. And next, we evaluated the algorithm based on the percent difference or percent error in the calculated petrophysical properties compared to the high quality values, which are shown in the first row in this table. So similar to the previous slide, we'll only touch on the bigger picture here. So overall, there is still not one algorithm that is most accurate across all properties. We also see, for example, that for porosity, which is a bulk property, the traditional filters, specifically the median and anisotropic diffusion, performed the best, whereas the Gaussian filter had the worst performance, which was around 14% error. And this can be explained by the blurring effect of the interfaces, making it difficult to locate the boundary between solid and pores, especially solid and brine interfaces, since their grayscale values are very similar. So on the other hand, we see that for most pore scale properties, fully and semi-supervised algorithms were the best performers, with the exception of a couple of them, and the analysis or the explanation of those is detailed in the paper. So some of the main conclusions out of this study are that the common filters show reasonable performance in terms of traditional evaluation metrics and bulk properties like porosity and saturation, but they result in significant errors in pore scale property estimates. There is also no single denoising algorithm that is most accurate across all petrophysical properties, but N2C and N2N75 showed an overall more favorable performance compared to the rest of the denoising methods. The semi-supervised method proposed seems promising to achieve accurate petrophysical characterization while still reducing scan time and cost. We also see that the qualitative evaluation and traditional denoising metrics are not always sufficient to select an appropriate denoising algorithm, and physics-based evaluation metrics would be necessary to decide on which algorithm to select. So it would be best to even have an independent measure of some of those properties for more reliable evaluation. And that's all I had for today, and I'd be happy to answer questions.
Thank you very much. So I was wondering, in terms of having not having the single best performer, one thing that I learned immediately: don't go unsupervised. So if you're not supposed to go unsupervised, in terms of like a future development where there would be immediate denoising done during the scanning, where would you inject the person checking in on the algorithm? Or is there, do you see in a foreseeable future a hope for developing something that is fully automated?
I can try answering this question. Miral, please correct me if I'm wrong somewhere, and Dr. Karpyn, yes, you can definitely add more to this. Okay, so a couple of things. Unsupervised is bad because we do not have a clear, clean signal for the network to learn from. Also, another big disadvantage of deep learning models is that they're very specific about what they're learning. They're not good at generalizing things to everything. For example, if we have learned on this particular data set, it'll perform well on only this data set. there is no guarantee that it would perform as well on every noisy CT scan of the soil sample. So what would be done in the future, I mean, at least in my view, is that you would have some samples of high quality and majority of them in low quality, and you would perform a semi-supervised kind of an approach that we have shown in the paper, where you would use the high quality, low quality pairs to learn, and you would use the learned model to apply, generalize it to the rest of your data set. So that is where I see it. And to talk about fully automating it, or whether a human is required somewhere in between, an expert is required in between, the expert, yes. So looking at a particular scan, these models are able to understand how much noise is in a particular given image of low exposure by simply understanding what a good high quality image looks like, what the ideal distribution of high quality images should look like. So in the paper, we have a particular image where we have shown histograms of clean samples and histograms of noisy samples. And one thing that's immediately jumps out is that noisy samples have this, grouped histogram where the modalities are not together. Like, you have these modes, these peaks of intensities, and they all kind of merge into one huge peak. And that is a very telltale sign of noise being in a scan. And networks can pick up on those kind of signatures, noisy signatures. Yes, this is exactly what I was talking about. And if you look at the particular scan, M, noise to noise, or even with the K, CC GAN, you will notice those peaks standing out individually. But whereas if you look at low quality LQ, it's just one huge peak that you have no information about the smaller peaks. So deep learning networks are trained to find such signs and push it towards multi-mode distributions. So I disagree that a human would be required, but I have to say yes, an expert would have to train it on that specific data set for that specific setting, and then the network would be able to do well.
Which is why it should sit in a scanning facility and see all of the samples coming in.
Yes.
Ankita, did you have questions? Unmute.
Yeah, thanks for the presentation. I think, it's nice to see the comparison that's being done for, the traditional filters that we use, because often that becomes the first step the moment we get our CD images before we even go ahead with segmentation. So I think that's a pretty standout thing. I think from my perspective, the one question I had is, when you're looking at semi-supervised learning, you said you use 75%, 50%, and I believe 25% of the information. So how did you go about choosing which information would the model see? Did you have to take care of the fact that it needed to see all the different phases in a certain number of images, or how did you go about choosing that?
For this particular case, we kept it completely random. We randomly sampled data. So for example, let's say we have 1,000 slices in our data set for our training. And among the 1,000 of them, we just say that 25% of them will have clean labels, or the remaining 75% of them will be given a noisy label. In the sense, the same image will be with a different noise realization, will be fed in as the target.
Okay.
It was completely random sampled.
And this was all done slice-wise, like sampling slices, or three-dimensional?
Yes. So it depends upon the model's size. For all the models that we have shown here, N2C, RDN, and CCGAN, we did slice-wise training, in the sense you have a slice as an input, a slice as an output. We have some reasoning for this. We did try patch-wise, which is more like we divided into 128 cross 128 patches and zoomed in. It's a better resolution for doing denoising. But then we faced some issues with that, specifically patching issues, in the sense once we patch it and denoise it, and then we unpatch it and we stitch them together, we noticed that on the boundaries of these patches, there were some boundary effects, and we were not able to get rid of them accurately. So in some way or the other, even during segmentation, we could see that these boundary effects were causing issues. There were certain intensity changes and things like that. So we decided to go with the training of the entire slice at once instead of doing it patch-wise. Yes, and that's why all this was patch-wise, slice-wise, sorry.
All right.
Yeah, and just one more thing. So, like, what did you find most challenging in your study, whether it's from the deep learning perspective or understanding what effect it has on petrophysics, or the properties? I mean, yeah.
Yep, I can start that one. So I would say one of the more challenging things was the quantitative evaluation using physics-based metrics, because that requires an extra image processing step between the denoising and calculating those metrics, which is segmentation, and that has its own inherent errors or uncertainties as well. So the way we approach that is we just first we tried to fix to train a model using ilastic, and then just apply it to all the different denoise data sets. But that didn't work initially because, as Amogh mentioned, as you apply all those filters, the histogram itself shifts, and we tried all different kinds of normalization to get them to be within the same range, but that didn't really work. So we ended up training a model for each of the different denoise data sets, but trying to maintain the same features that we included, as well as the same number of samples or seeds that we used.
Okay.
In absolute sense, grayscale value they don't mean much. So they can be shifted and changed and normalized in more ways.
Yeah, so if you think about it, it's in the end, I can have arbitrary values to those regions as long as I maintain the relative distance between the two regions the same throughout. But unfortunately, with elastic, what was learning was the absolute position in the histogram scale. And so even slight changes, it was too sensitive to that, and it was not recognizing something as a particular region. If you could show an example, Miral, of a slice, I can explain it a little more. Yes, for example, you see the darkest region. Could you go back? Yeah, this one. Yeah, this is perfect. So you have the CO2, supercritical CO2 there, and which is very close to the background class, which is black. It is not the same, but it's very close to it. So a lot of times we would have the supercritical CO2 go very close to black in our denoised images, and the elastic model would assume that it's also the background class, and in the segmentation would go wrong horribly. And those issues were hard to fix. Yes.
All right. So just to conclude, this is only one study in Zuleima's very long career in using X-ray imaging to study subsurface problems. So would you briefly just describe what is your research group currently working on? What are some of the major efforts?
Absolutely, I'd be happy to, Masha. Thank you for the opportunity also to present this. And before I get to the big picture, something else I wanted to add about this piece of work is that whenever you present a comparative study where you're trying to assess performance of a combination of different denoising algorithms, inevitably, you're trying to find the best performer across all measures of assessment. But when the reality here, I think, is one of the biggest contributions is to be able to provide information how to inform the user of these techniques to identify the trade-offs, right, of what would be best under which conditions and what you're trying to achieve, because there isn't a single approach that will work fail-proof across the board. So I think that piece is very valuable here. And part of that trade-off, which is not captured here necessarily in the paper, is a trade-off of having to train your own research group. Maybe all you know are their traditional filters, and that's good enough for the measurements that you want to take, and that is fine. But being able to have that bigger picture of what's possible and what potential gain you can get on your data can be useful. Where to take this from? I think an immediate step connects to what Miral and Amogh mentioned about connecting with the segmentation piece. We've worked independently on assessment of performance using deep learning algorithms for segmentation. and we've developed similar matrices for segmentation alone, and we're trying to integrate the entire workflow. So trying to automate as much as possible, not only at the upstream, we're trying to obtain the data and denoise, but throughout the entire connector workflow, from data acquisition, denoising, segmentation, and ultimately finding those physical properties. So that's one dimension in which we're working on as an immediate next step of this work, and all of that in the context of finding better ways to determine properties of geomaterials in the context of flow, and that feeds into that kind of bigger agenda of my research group.
Thank you very much. And thanks everybody for joining us. And we're looking forward to many more exciting data sets posted on Digital Rocks portal. Thank you.
Thanks.